Hello! In this video, we present the retrosynthesis of diazepam, which is isotopically labeled with 2 deuterium atoms. This isotopologue could prove useful for investigating the pharmacology and metabolism of this drug, as an internal standard for bioanalytical methods. The retrosynthesis of di-deuterated diazepam involves considering unlabeled diazepam as the primary precursor and fully deuterated methanol as the deuterium source. The unlabeled drug, for its part, is prepared from commercially available raw materials, as we will see later. This retrosynthesis begins by considering that the 2 deuterium atoms are attached to an alpha carbon, to the lactam's carbonyl group. First, the indicated nitrogen is protected to generate the deuterated N-oxide 2 through a functional group transformation. 2 carbon-deuterium disconnections in 2 generate the oxiderivative of diazepam-3 and the fully deuterated methanol as a raw material and deuterium source. These disconnections are based on the possibility of forming the corresponding enolate intermediate. This allows the introduction of deuterium atoms into the heterocyclic ring coming from the deuterated methanol. A functional group transformation of compound 3 generates the unlabeled diazepam, compound 5. A carbon-nitrogen disconnection leads to the formation of 6-methyl iodide as a raw material. The imino group in 6 functions as a retron and through a carbon-nitrogen double bond disconnection, based on an addition-elimination reaction, opens the heterocyclic ring, generating aminobenzophenone 8. The primary amino group in 8 functions as a retron, based on a nucleophilic substitution. Thus, a carbon-nitrogen disconnection gives rise to compound 9 and ammonia as a raw material. The amido group in 9 functions as a retron and a carbon-nitrogen disconnection produces aminobenzophenone 11 and chloroacetyl chloride as raw material. Considering that compound 13 is a tautomer of 11, the proximity between the hydroxyl group and the imino group suggests the possibility of forming a bond to create a heterocycle. Following this particular line of reasoning, a nitrogen-oxygen connection generates the benzisoxazole 14. A carbon-oxygen disconnection in the hetero-bicycle 14 gives rise to the cyanoderivative 15. A functional group transformation oxidizes the hydroxyimino group present in compound 15, leading to the formation of compound 16, whose tautomer is the cyano-nitrobenzene number 17. Because of the ortho relationship between the nitro group and the cyanobenzyl fragment in 17, a carbon-carbon disconnection generates chloronitrobenzene 18 and phenylacetonitrile 19 as raw materials, based on an aromatic nucleophilic addition reaction occurring at the ortho position with respect to the nitro group. In summary, the main disconnections are shown here. In the following video, the resulting synthesis will be presented.